Okay, so welcome back to the second part of lecture 8, where we talk about boosting, well, ensemble boosting, but you can just call it boosting. So boosting is a really clever idea, and it's one of my favorite ideas in supervised machine learning. And so, well, what is it? Boosting is an ensemble method that trains predictors sequentially, each trying to correct the errors made by the previous predictor. So in this lecture, we're going to consider two boosting algorithms or methods. There's many more, but we're only going to consider two, called Adaboost and gradient boosting. We're going to focus on gradient boosting because it, to me, is the most intuitive. But on Canvas, I provided a link, and I think later I'll put a link for a video going into the details of Adaboost. But at the very least, I'll show you how to implement it using scikit-learn first before we talk about gradient boosting. Okay. So the general idea, so with Adaboost, is that the training algorithm first trains a base classifier and uses it to make predictions on the training set. Then each of the misclassified training instances is then given a relative weight. So at the very beginning, all the training data points have the same weight. But then this base learner makes predictions and gets this one wrong, maybe this one wrong, okay? The next classifier is then trained on the data set using these relative weights. So the weights are like saying that these points that we got wrong are more important. So we need to like consider those. And the way that I like to think about how the base learners are chosen is with each feature. There's like a decision stump on each feature, right? And it's trying to find the best one on the x-axis, the best one on the y-axis that it can do. And then it makes poor predictions possibly on this data, on these data points, on these data points, on these data points. So then the relative weights of these points that were misclassified is increased. And then also there's a weight that you can assign to the classifier on the x-axis and versus the classifier on the y-axis. And again, the video that I provided on Canvas, I think describes it really well. But the idea, which will become very apparent when we talk about gradient boosting, is simple. You have learners that are trained, and then the next learner tries to make up for the deficiencies of the first one. And the next learner tries to make up of the deficiencies of that one. And then you can aggregate them together at the end and give them relative weights of how important their votes are in the classification task. So as we did before, we're going to look at this particularly hard case of Virginica and Versailles color flowers from the iris data set. I suspect we won't do any better than what we just saw because 90-something% accuracy is pretty good, but I just want to see. All right, so I'm just going to load the data and view it. There's that difficult classification task. And then we're going to do a train test split, and we're going to look at the scikit-learn Adaboost classifier. Okay, so I imported the decision tree classifier because Adaboost requires a base learner, okay, to pass in there. Now, I put in decision tree, but you could put in whatever binary classifier you want. You could put in logistic regression if you wanted. You could put in the perceptron, like anything, right? So the number of estimators, I'm gonna say is 10. This can increase, but let's just say 10 for now. And this is the algorithm that we're going to use. We have to pass it a type of algorithm for it to train on. We don't have to, it's a keyword argument, but this is essentially this like, it's the most optimal solver that they have to solve this. And then the learning rate, we're going to talk about in detail when we get to gradient boosting. Okay, so we instantiate our classifier and we fit, make a prediction, and then look at the classification report. 75%. So for those two features, that was the best we saw earlier, right? And I doubt anything will change if we make this like 100. Should still be, it went down, right? So, and that's because we're not truly like looking at, like we're not ensembling everything in the way that we were doing it in lecture 9.1. Each learner is being weighted, right? And it's like, the best way to describe it is that if you have a bunch of them, the final like a bunch, like you have like 100 base estimators, then a lot of them, because they're weighted, are going to have like very little votes to them, and you're going to get like skewed behavior because of that. And the best way to learn about it really is to just experiment with it and like plot what happens with the accuracy as you increase the number of learners. And that would be like a good thing to put on one of your projects, right? To look at how that affects the behavior of the accuracy of this type of learner. Okay. So let's look at the decision regions though. Like, what does that look like? Okay, that's not bad looking to me, right? Still, like, even though that decision tree was doing well in the previous lecture, like that's concerning to me. For if we start observing more data points, that's very concerning to me. But yeah, I like this. This is kind of nice. That one point right there really skewed things though. You see that? Like really skewed it. Okay, so let's see how this behaves when we have 4 features to look at. Okay, everything should be the same. I don't know why test train split occurs twice. There, fit it, look at the report, 88%. So that's close to like the best we saw with the other types of learners, right? But really, I think to understand how clever this idea is and how it can work, right? Like right now we're looking at a very difficult problem of classification. Like trying to get anything above 90% is going to be very hard. And I don't think we're going to do it right now. But I think the idea is the important thing for these boosting algorithms. So gradient boosting is the most natural for me to understand. So this method works by sequentially adding predictors to an ensemble, each correcting its predecessor. So there's no weighting going on. It's just trying to correct its predecessor. The difference between this method and Adaboosting is that gradient boosting tries to fit a new predictor to the residual errors made by the previous predictor. Okay, so we're going to denote residual error by error, right? So suppose we have given features X and regression values Y. So we're doing regression now, okay? And we train our first regression tree. It'll be a regression stump, basically. And after training, this thing predicts, this should be a 1 right here, sorry, right here. This regression stump predicts Y hat 1 of like real values, right? So then the true values, right? The true real labels is denoted by Y. So this is equal to our predictions plus some error term, right? Like we're not going to get perfect answers. There's going to be error here. So that error is equal to Y minus Y hat, right? Now think about this. So we have these errors, right? And if we knew these values and we put them right there, then we'd have exactly Y, right? So why not train another base learner to learn the errors, right? So if we can learn those errors and we just add it on, we have a better prediction, right? So then we set Y2 equals to Y minus Y1. That's the errors, right? And then train a tree with those targets. And that tree will make predictions Y hat 2. So then error 1 is equal to Y2, right? Which is equal to Y2 hat plus some other error term, right? So then if we plug this back in to the original equation, we get that Y is equal to Y1 hat plus error 1, which is equal to Y1 hat plus Y2 hat plus error 2. And what will happen is that error 2 is smaller than error 1. And we repeat this. We repeat this over and over again. So what's going to happen is that the sum of the predictions when we do this is going to become a better and better approximation to the true labels. So it's kind of like clever, right? Like we know that there is some like error here. Let's just learn what that is. And then there's another error. Learn what that is. Learn what that is. Learn what that is. So let's go ahead and make some artificial data to view this. And so currently, we wouldn't have a single model like a regression tree might do okay on this maybe, but regression trees are prone to overfitting, right? We could use linear regression and square the term and have that as like one of the entries, right? But let's see what happens if we just use a bunch of base learners. So regression tree with max depth 2. That's not a stump, but it's almost a stump, right? So because this, oh, I didn't explain to you this code. So I set my random seed to be 0. So this is like, I can reproduce this. I make a linspace of x values, and then my target values are those values to the power of 4, plus some noise taken from a normal distribution. That's why if there was no noise, it would just be a curve, a quartic curve. But I want to add noise to make it difficult. So in that case, x here is it's a one feature type of vector. So that means we have to reshape it for scikit-learn to take in, make it into a column vector form. I call it x new. I don't know why I chose to do that, but that's what I did. So then I train a regression tree with max depth 2 on the training data here. Okay. Once I do that, I set y2 equal to y train minus the predictions from my first regression tree. And then I make a second regression tree, same exact type of tree. And I fit it with the X data that we have, but now the numerical labels are the residual error terms. And then Y3, it's my new residual error. And then I fit again to that. So there's 3 of them. Okay. Now this code here I commented out, this is just a way of writing the full predictions, just the sum of the predictions. But I thought it'd be more illustrative to actually write it in the plotting code so you can see it. So here I make a subplots. I call the subplots method. It's going to be 3 wide, 1 tall. So in the first plot, it's our first predictor. In the second plot, it's the sum of these 2 predictions. In the third plot, it's the sum of the 3 predictions. So you can see that it's starting to get better, right? And that's because like theoretically, we're just like approximating that true error term. We're learning it. That's what we're doing. We're learning the errors at each term. So if we keep on doing this, we're closing the gap, right? So this is doing it manually. Of course, scikit-learn has a built-in functionality for this. So from sklearn .ensemble import gradient boosting regressor. And then I'll use gradient boost regress equals to, so I need to instantiate it. Max depth equals to 2. Number of this will do the exact same thing. Number of estimators equal to 3. And then learning rate, and I'll explain what that is in a moment. 1.0, and then random state 42. And then y predict equals to, how did I do BG? It should be GB. GB regress dot predict on next new. Oh, I didn't fit it. I got ahead of myself. gv reg dot fit x train y train. So then if I wanted to look at the plot like this, it's like the exact same thing. So maybe let's copy this and do a quick one. dot.scatter, dot.plot, dot.show, and then it's going to be all small, so I need to fix that. dot.figure fig size equals 10 by 8 or something. Maybe it isn't. Oh, well, I should probably speak about what this learning rate is. So the learning rate is a way of scaling the importance of the other learners. So there's like a sequence of them, right, that are appearing. The learning rate is going to scale their predictions. And the further down the line it gets, like the smaller it'll be depending on the learning rate you have. So like if I change this learning rate to be like 0.2 or something like that. And then look here. Oh no, what am I doing? Right, that's why it looked the same. gv reg. So now it looks different. Let me put this learning rate back to 1. So all of them get the equal vote as we did above. So there. Okay. It's kind of cool though, right? It's a neat idea. And you can see that it's like, there's lots of noise right here. And to me, like viewing this, it's nice, right? In that region. And then when there's not lots of noise, it's like kind of around it. So this, to me, looks very good because it's like it learns that there's lots of variation in the data right there. And it just kind of split it down the middle. One thing that you have to be like aware of though is, again, these are like almost like orthogonal splits, right? Like the connecting lines, there's curve there, but really the predictions are points, right? And those points are these like these splits here. Okay. Now, let's see what happens if we change the number of estimators to be like 150. I wonder what's going to happen. That's like highly overfit looking to me. Look at it, right? So one way that we can kind of like maybe make it less overfit is by saying that the regression trees down the line in the sequence have less voting power with the learning rate. So I can decrease the learning rate and maybe make that look a little bit better. Still, there's so many of them. Make a really small learning rate. That kind, okay, decreasing it to 0.05 kind of did what I wanted it to. There's still way too many learners, right? I'd maybe say like, okay. Now, it's kind of nice, right? Yes. Yeah, so like really like what I should have done is this X train. Let's look at that. No, not train, test. That's what I should have been doing. I apologize. So what was it? It was 150, and this is like It's like 1, right? So test, 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 test. Let's see. Oh no, the ordering's off. And that's going to be a pain for me to do real fast. The reason why it's doing that is all the ordering is off. Let me actually pause the recording and fix that real fast. So, because when you do the train test split, it's randomly picking them, right? So then it's no longer in sequential order. So that visualizing that, I'm thinking about the best way to do that real quick. Oh, I know what to do. So okay, so this is going to take me a second, but I will get this fixed. Okay, so y predict that, and then points equals x for x and zip x test. You'll see, you'll understand why I'm doing this in a moment. Y predict points. Points. Okay, those are the x value, y value, x value, y value. So then points dot sort, and then do p lambda x goes to x. Actually, let me fix this real fast. For x comma y. Let me just get rid of this. Yep, okay. So then dot sort equals lambda x 0. Oops. All right, so now with all that work, I got I got it sorted. And they're like paired together appropriately. So do you understand what this code is doing? I zipped them together, and then I sorted with the keyword like this because they're tuples, and I'm sorting by the 0 entry. So then I can do like x new test equals np dot array, and then do x0 for x in points like that. And then y new test np dot array x1 for x in test, or no, points. And then x new test equals x new test dot reshape -1 1. Sorry, it's taking so long. And then y new. Yeah, okay. So I guess I didn't pause the recording. I guess I just been going. Okay, so that's fine. So you saw me figure it out in real time. So big size, do 10 by 8, PLT dot scatter. Oh, that's what it was. Screen sharing is paused. So, oh, there it is. Okay, so, all right, well, I got to figure it out now. I'll just cut the little out. So it was unordered because when we do the shuffle split, it like picks randomly. So that's why the lines are all over the place. So to fix that, I make y prediction equal to the gradient boost predict on x test. And then I make a list of tuples coming from x test and y predict. That way the x and y values are paired together. Then I sort by the x entry because that's how we're going to plot them. And then I make NumPy arrays of the x values and the y values so they have the same indices. I reshape because it's a single feature vector. I might want to use that later. And then I'm going to scatter x new test, comma. Well, in any case, that's going to take a second to do because, well, no, it's not going to take a second. I have y, z or whatever, x, y, z. And then here I'll put in y test. So they're all like together. Sort by the x entry and then y. So you predict, right? And then here, y new test. So I just have to copy that there. It's getting kind of long, but I'm just doing this on the fly, kind of hacking it together. There, y new test, y new predict. Please work. Okay. All right, color equals to red. Dot show. Okay, so that's it's not the best, but you can see that this like I hate looking at that now. Let me just get rid of that. So let's like what happens there's like 250 of them. And then reviewing the plotting on that. Okay, so these like this like again these are like predicted points, right? They're connected by a line, but like we're predicting like up here, right? We're predicting like way up here for that point, right? That one we were kind of close to, but like that point we predicted there, so that's not good. Right? But if we like severely, there's probably way too many learners. I'll go to 150 again. It was like 0.02. Train again. Better. Without even looking at the mean squared error, like I can just visualize and see that's better. And I'm a big proponent of visualization with these things. It's like giving me like intuitive sense of what's happening. Maybe if I increase the learning rate, see what happens. I don't know. We'll see. Again, we start getting that jagged behavior again. And we're really trying to like kind of smoothly approximate it. It's a quadratic, right? Like it's not supposed to look like that. There's noise, but we really want that quadratic there, or not quadratic, quartic, right? It's a quartic function that's making that data. So, okay, just something to keep in mind. Also, I'm not going to touch on it right now, but there is like a I might have it, I probably don't. XGBoost package, I don't have it, but this is like a highly optimized gradient boost package that's not included in sklearn. It's its own package, and I encourage you to go and look that up and check it out. Okay. Okay, and then again, as with the decision tree chapter, like definitely read this ensemble chapter. Okay, and the problems are good. Right, so check out the problems in that section as well. All right, so I'm gonna go ahead and stop the recording here.